Good day and welcome back to the first part of our discussion on the fundamental theorem of line integrals. To begin, let me remind you of another fundamental theorem that we've encountered in the past and used multiple times throughout our calculus experience. That would be the fundamental theorem of calculus, which tells us to evaluate a definite integral, all we need is an antiderivative of the integrand. And this is written in a somewhat ideal form because an antiderivative of big F prime is simply big F. So we evaluate it at B minus sign evaluated at A. Something you've probably done hundreds of times at this point. Now, in order to use a fundamental theorem of line integrals, we will need a conservative vector field. So let me remind you that a vector field is conservative if big F is a gradient vector field. So just to repeat that, a vector field is conservative if it is a gradient vector field. And also to make sure that we are all on the same page, if we have a function of two variables, little f, the gradient of f would be a vector with two entries made up of those corresponding partials. And the idea can, of course, be generalized to a function with as many variables as we would like. Now that we've had a few reminders, let's go ahead and state the fundamental theorem of line integrals, which I will abbreviate whenever possible as ftoli, and you are certainly more than welcome to do so as well. So if we have a curve C given by a parametric description R of t, under some reasonable restrictions, we have the following formula. The line integral over a gradient vector field of a curve C is defined to be f, so note f is the potential function of the gradient vector field, and it's f of R of B minus f of R of A. And just to make an observation, we're thinking that we have a curve C, which we've described by this vector valued function R of t. So there's a small abuse of notation where this vector R of A, I'm thinking of the point associated with it, the beginning point of the curve. And the ending point R of B is being represented by this vector R of B. So note the similarities between the formula we have for the fundamental theorem of calculus and the formula we have for the fundamental theorem of line integrals. We need a potential function, little f, playing the role of an antiderivative. We evaluate it at the end point of the curve. We subtract away that function evaluated at the start point of the curve. And one thing I will ask you to do is whenever we use the fundamental theorem of line integrals, you should indicate to me that you are using it. And that is as simple as just writing an ftoli over the equal sign when you apply it. And it is also really important to note that when we are applying the fundamental theorem of line integrals, the curve itself wasn't really important. The important features of the curve was where do you start and where do you finish. So as long as you know the start point and the finish point, we can evaluate line integrals over a conservative vector field. Because remember, a conservative vector field is a gradient vector field. So let's go ahead and look at an example. For a function of three variables, given by cosine pi x plus sine pi y minus xyz, and c being any path starting at the point 1, 1/2, 2, and ending at 2, 1, minus 1, let's evaluate this line integral. And the wording of the problem, along with the form of the integrand, is indicating that we want to use the fundamental theorem of line integrals. So we're told specifically that we're integrating a gradient vector field, but we're also only given a starting point and a finishing point, which is a hint to apply the fundamental theorem of line integrals. So in terms of our line integral of interest, the fundamental theorem of line integrals, which I'm going to let the reader know I'm applying by writing a few letters over the equal sign, tells us that we get back the potential function f evaluated at the end point minus the potential function f evaluated at the starting point. So in terms of our above work, we're thinking of r of a as being the starting point, 1, 1/2, 2, and 2, 1 minus 1 as representing r of b, that finishing point of the curve. So f of 2, 1 minus 1 minus f of 1, 1/2, 2. And without using any of our previously discussed techniques, we are able to evaluate the line integral over this conservative vector field by performing two function evaluations. So in the first case, f of 2, 1 minus 1 is cosine of 2 pi plus sine of pi minus 2 times 1 times minus 1. So I'll go ahead and just say plus 2. And then we subtract away cosine pi plus sine of pi over 2 minus 1 times 1/2 times 2. So minus 1. And if we go ahead and just take care of these common values, cosine 2 pi is 1, sine pi is 0, cosine pi is minus 1, sine of pi over 2 is positive 1, what we end up with is 1 plus 2 minus a minus 1. So the value of this line integral is 4. And at this point, the takeaway should be, if we have a line integral over a gradient vector field, i.e. a conservative vector field, as long as we can find the potential function and we know where the curve starts and where the curve finishes, it can be a very quick and efficient line integral to evaluate. So to summarize, if big F is a conservative vector field, in order to evaluate the line integral over a conservative vector field, and note, to say this is conservative means that big F is the gradient of some function little f, and we can evaluate this line integral simply by knowing the value of our potential function little f at the endpoints of the curve. And let's finish by making one more observation. If I was to sketch a curve going from some starting point A to some finish point B, and let's just think of this curve as being C1. And what I want to observe is that if we have a conservative vector field, so if big F is conservative, and we want it to evaluate the line integral over the curve C1. And what I want to observe is that there's nothing special about this curve C1 when it comes to evaluating the line integral. That is to say, if we had a separate curve, and I'm drawing something rather extreme looking, call it C2, connecting A to B, that would give us the same exact value. So the curve itself is irrelevant as long as it starts at one point and finishes at the other. And because the curve itself is not important to evaluate this integral, it's just the start and finish point, we refer to this as being independent of path. And we've seen language that indicated this in our previous example when we are told we are considering any path starting at one point and finishing at another. So we will continue on investigating the fundamental theorem of line integrals in the next video. So stay tuned and take care.